A few years ago, I was standing inside a barn in Essex, England, a building called the Barley Barn at Cressing Temple. And I want you to understand something about this structure. It was built around 1215, that is over 800 years ago. The roof had never been replaced. The frame had never been rebuilt. And every single joint in that building was held together with nothing but shaped wood, no screws, no nails, no steel brackets, just oak meeting oak, locked together with wooden pegs. Meanwhile, I have got a deck at home that is 15 years old, and half the lag bolts are already rusted and working loose. That contrast stopped me in my tracks. Today, I'm going to walk you through exactly how medieval joiners built connections that outlast anything we are using now, and why their methods still beat modern screws and brackets. Plus, stick around to the end, because I will show you a peg shaping trick from the old timber framers that makes every joint you build tighter from day one. Let me show you what I found. What we are really talking about today is medieval timber framing. Not as a history lesson, but as engineering that still works. These methods held together cathedrals, barns, and homes for centuries, and the principles behind them are things any woodworker can use right now in a home shop. So let me start with who these builders were, and why their approach deserves your attention. When we say medieval timber framers, we are not talking about a handful of master craftsmen in one workshop somewhere. This was the standard building method across England, France, Germany, and most of Northern Europe from roughly the 11th century through the 16th century. Every town had timber framers. Every village had men who understood these joints. It was as common then as stick framing is today. And these were not scholars or artists. They were working tradesmen solving structural problems with the materials they had available, which was mostly oak, green oak, fresh from the tree, still heavy with moisture. What impressed me most when I started studying this was how practical their thinking was. They were not trying to build monuments. They were trying to build structures that would survive in a climate with harsh winters, heavy rain, constant humidity swings, and in many regions, real wind loads. They did not have steel. They did not have engineered lumber. They had axes, chisels, hand braces, and a deep understanding of how wood behaves over time. And that understanding is what made the difference. They knew that wood moves. They knew it shrinks, swells, twists, and settles. And instead of fighting that movement the way we do with rigid metal fasteners, they designed joints that work with it. Joints that actually get tighter as the wood seasons. That is not poetry. That is engineering. And once I understood the thinking behind it, I started seeing every screw and bracket in my own shop differently. Now, before I show you what they did, I want to talk about why the modern approach fails, because most of us reach for screws and metal brackets without ever questioning whether they are actually the best connection. And I was the same way for decades. A screw feels strong. You drive it in, you feel that bite, and you think, that is solid? That is not going anywhere. But here is what is actually happening inside that joint. A screw is a rigid metal shaft locked into a material that is constantly moving. Wood expands and contracts with every change in humidity. Even inside a climate-controlled house, the moisture content of your lumber is shifting with the seasons. And every time that wood moves, it is pushing and pulling against a fastener that cannot move with it. The screw does not flex. The screw does not compress. So instead, the wood fibers around the screw get crushed, torn, and slowly wallowed out. That is why screw holes get loose over time. The screw did not fail. The wood around it failed because the connection was never designed to accommodate movement. Steel brackets have the same problem, just on a larger scale. A bracket is a rigid plate bolted to two pieces of wood that are both moving independently. Over time, the bolts loosen, the holes elongate, and the bracket starts rocking. Add moisture exposure, and you get rust, which expands the metal, which cracks the wood further, which accelerates the loosening. I have pulled brackets off of 20-year-old deck posts that practically fell out in my hand. The steel looked terrible, and the wood around the bolt holes was soft and punky for a full inch in every direction. Now compare that to what I saw in that 800-year-old barn. The oak had turned iron hard with age. The joints were still tight. No corrosion, because there was no metal to corrode. No wallowed-out holes, because the connection was wood-bearing against wood across a broad surface, not a single point of stress. The load was distributed across the full cheek of every mortise, the full shoulder of every tenon, and the full diameter of every wooden peg. That is a fundamentally different kind of connection, and it is why those buildings are still standing while our modern fastened joints are being replaced every couple of decades. So let me show you the joint that did most of the heavy lifting in medieval timber framing: the pegged mortise and tenon. Now, most woodworkers are familiar with the basic mortise and tenon. You cut a rectangular pocket in one piece, shape a tongue on the other piece to fit into it, and you have got a strong mechanical connection. But the medieval version takes this further in ways that matter. First, the scale. These are not the delicate furniture joints most of us practice. A typical medieval timber frame joint uses a tenon that is 2 inches thick, 4 to 5 inches wide, and 4 to 6 inches deep into the mortise. The timbers themselves are often 8 by 8 inches or larger, hewn from green oak with a broad axe and finished with a slick, which is essentially an oversized chisel about 3.5 inches wide with a long handle that you push rather than strike. The fit is what matters most. Medieval joiners cut their mortises first, then scribed and trimmed the tenon to match. The cheeks of the tenon, the broad, flat faces, were fitted tight against the walls of the mortise so that you had maximum wood-to-wood contact. This is where the strength comes from. It is not the peg holding the joint together. The peg's job is to keep the tenon from sliding back out. The actual structural load is carried by those cheek surfaces and by the tenon shoulder, which is the flat face where the tenon piece butts up against the mortised piece. They bored a hole through the assembled joint using a hand brace with a spoon pattern auger bit, typically 3/4 of an inch to 1 inch in diameter. Then they drove a wooden peg through that hole, usually made from riven European beech or sometimes oak. Riven means split along the grain, not sawn, which keeps the grain fibers continuous and makes the peg dramatically stronger. A riven peg can handle shear loads that would snap a sawn dowel of the same diameter. The result is a joint with no metal, no glue, and no weak points. Every component is wood. Every component moves at roughly the same rate with humidity changes. And every component shares the load across a broad area instead of concentrating stress at a single point. By the way, if you are enjoying learning about these old-world methods, I put together something I think you will really appreciate. It is called The Old Ways, and it is a collection of 100 forgotten woodworking secrets from traditional craftsmen around the world. Techniques like the ones we are covering today, and a whole lot more. You can grab your copy by scanning the QR code on screen, or just use the first link in the description. All right, let us keep going. Now here is where medieval joinery gets truly clever. And this is the technique that really changed how I think about building with wood. It is called draw boring. And once you understand it, you will wonder why anyone ever stopped doing it. Here's the concept. When you bore that peg hole through the mortise and tenon, you do not line the holes up perfectly. Instead, you bore the hole through the tenon about 1/16 to 1/8 of an inch closer to the tenon shoulder than the hole through the mortise. The holes are deliberately offset. So when you drive the peg through, it has to bend slightly as it passes through the misaligned holes. That bending force pulls the tenon tight into the mortise and holds it there permanently. Think about that for a moment. There is no clamp. There is no glue. The peg itself is acting as a permanent clamp, pulling the joint tight with mechanical force that never lets go. I have driven drawboard pegs into test joints and tried to pull them apart, and I can tell you, they are not coming apart. The force required to reverse that peg is enormous because you would have to bend the peg back through the offset, and the wood fibers have already compressed and locked around it. The process is straightforward but requires care. You cut your mortise, fit your tenon, and bore your hole through the mortise walls with the tenon removed. Then, you insert the tenon, mark where the hole lands on the tenon cheek, pull the tenon back out, and bore the tenon hole offset toward the shoulder by that 1/16 to 1/8 of an inch. Reassemble the joint and drive your peg. As the peg enters the offset hole in the tenon, you will feel the joint cinch tight. The shoulder pulls up hard against the mortise timber, and that is where it stays. Medieval framers did this on every structural joint in the building. Every knee brace, every tie beam, every principal rafter connection, hundreds of drawboard pegs in a single frame, each one pulling its joint permanently closed, and 800 years later, those joints are still tight. Try finding a screw that can make that claim. Now let me show you another joint that medieval framers relied on for a completely different problem: the scarf joint. This is what they used when they needed a timber longer than any single tree could provide. Instead of butting two beams end to end and bolting a plate across the splice, which is how we handle it today, they interlock the two pieces with shaped faces that resist pulling apart, resist bending, and distribute load across a long section of overlap. The most common version I have encountered in English medieval frames is the edge-halved scarf with bridled abutments. That sounds complicated, but the concept is elegant. Each timber is cut with a long diagonal face, typically 18 to 24 inches of overlap for an 8-inch timber. The diagonal faces have step notches cut into them that interlock when the two pieces come together, preventing any lateral or vertical movement. Then, the whole assembly is pegged, often with 2 or 3 drawboard pegs. The genius of this joint is that it turns a splice into something that behaves almost like a continuous timber. The long overlap means the bending forces are spread across a wide area. The interlocking notches prevent the two halves from sliding apart, and the drawboard pegs hold everything tight while the wood seasons and shrinks. I have seen scarf joints in medieval roofs that you cannot even find unless someone points them out to you. The two timbers have settled together so completely that the joint line has virtually disappeared. Compare that to a modern steel splice plate bolted across two beams. The bolts create stress concentrations. The plate adds weight. The connection is rigid where the wood wants to flex. And in 20 or 30 years, you are looking at rust stains, loose bolts, and cracked wood around the holes. The medieval scarf joint just sits there, getting tighter, doing its job, century after century. There is one more principle that ties everything together, and it is the reason these joints actually improve with age. Medieval framers worked almost exclusively with green oak. That means freshly felled timber with a moisture content of 60% or higher. To a modern woodworker, that sounds like a terrible idea. We are taught to dry our lumber before building with it. But the medieval framers understood something that we have mostly forgotten. Green oak is soft enough to cut cleanly with hand tools. You can chop a mortise in green oak in a fraction of the time it would take in seasoned oak. The joints fit together easily because the wood is pliable and forgiving. But then, over the following months and years, that green oak dries and shrinks. And as it shrinks, the tenon gets tighter in the mortise. The peg compresses and locks harder into its hole. The shoulders pull closer. The entire joint effectively clamps itself with a force no mechanical clamp could maintain for that long. This is why those 800-year-old joints are still tight. They were designed to use the natural drying process as a permanent clamping mechanism. The wood did the work. All the joiner had to do was understand the process and trust it. European white oak, the species used in most English and French medieval frames, shrinks about 7% tangentially and 4% radially as it goes from green to fully seasoned. That is a significant amount of compression being applied to every joint surface, and it never lets go. Let me share some patterns I've noticed over the years, things I used to do myself that this tradition handles completely differently. The first pattern is reaching for metal fasteners by default. Most of us grab a box of screws before we even think about how a joint could hold itself together. It is automatic. But every screw is a stress point that fights the wood instead of working with it. Medieval joiners never had that option, and their work outlasted ours by centuries. The second pattern is demanding perfectly dry lumber before starting a project. I kiln-dried everything for years because that is what every book told me to do. But what I learned from studying green oak framing is that moisture is not always the enemy. Sometimes it is the mechanism that makes the joint work. There is a time and place for green wood, and ignoring that means you are ignoring one of the most powerful clamping forces available to you. The third pattern is designing rigid connections. We bolt things tight, glue things flat, and expect nothing to move. But wood moves. It always moves. Medieval joiners accepted that from the start and built connections that flex and accommodate instead of resist and crack. Once I started thinking about movement as something to work with instead of fight against, my joinery got better almost immediately. The fourth pattern is valuing speed over longevity. A pocket screw takes 30 seconds. A drawboard mortise-and-tenon takes an afternoon. But one of those connections will be tight in 50 years, and the other will be loose in 5. I am not saying every joint in your shop needs to be drawboard, but for anything structural, anything that matters, the time investment pays for itself many times over. Now, for that bonus tip I promised at the beginning. This is a peg shaping technique I picked up from a timber framer who learned it from his father, who learned it from an old English framing tradition. When you make your pegs, do not just whittle them round. Start with a riven blank of straight-grained beech or oak, about 1 inch square and 8 inches long. Shape it roughly octagonal with a draw knife, then taper just the leading inch to a gentle point. But here's the key. Leave the last 3 inches of the peg very slightly oversized, maybe 1/32 of an inch larger than the hole. As you drive the peg, that leading taper finds the hole easily, but the oversized trailing section compresses into the surrounding wood, creating a friction lock along the full depth of the joint. The old framers called this a compression fit, and it means the peg is not just passing through the hole, it is actively gripping every inch of the way. I started doing this about 3 years ago, and the difference in how solid the joint feels when that peg seats is immediate. You feel it in your hands when you swing the mallet. The peg stops with authority. Before we wrap up, if today's video taught you something new, imagine having 100 techniques like this at your fingertips. That is exactly what the old ways is. It is my collection of forgotten woodworking secrets from the world's greatest traditional craftsmen, all in one place, with 75 photos and clear instructions. You can get your copy by scanning the QR code on screen or using the link in the description. Thanks for being here. Subscribe if you have not yet, and I will see you next time. Those medieval joiners figured this out 800 years ago with hand tools and green logs. The strongest connection in your shop might just be the one with no metal in it at all. Thanks for spending this time with me. I will see you in the next one.